How's it going? Great. Somehow hot in here, rainy outside. The weather can't make up its mind at all. All right, so let's talk about diffusion models. It is election day, so if you have to vote, you have my permission to skip this class. Hopefully everyone already voted. Let's do some brief announcements. So homework free has been out. That's due in 1 week. Project dates are going to be November 21st, so a few weeks from now, for the proposal. And then end of class, December 13th, for the report. Folks have mostly signed up now for all of our different presentation dates. The only really kind of pressing deadline is that on Thursday, we have the presentation proposal due. I have made Canvas upload things for these, so folks who've already done this and they're ready, you can go ahead and submit it. We are also kind of at the very end of our class. So we have today's lecture, and then we have kind of the, mixed category of topics that we haven't gotten to for Thursday. And that's about it. So we're almost done with me presenting. The rest will be you guys talking about kind of more advanced papers. Any questions about any of these logistics? Yeah?
So should every group member submit on Canvas?
Oh, that's a very good question. Let's actually just do one here. I'll go through and mark everybody who's part of the group separately. But just so I don't have to have like many different copies of every single proposal, presentation, et cetera. All right, so everyone got that? You can just submit one person from a group. Everybody else does not need to. Cool, good point. Any other logistical questions? Yeah, if anybody needs to start kind of testing their setup for their presentations, come chat with me. We can use a little bit of time either today or on Thursday to test out your computer. Or we can just do it in real time on Tuesday, Thursday, next week, and so forth. I will be keeping track of time, and I'll probably be pretty aggressive about enforcing it just to make sure everyone gets a chance to go. Last year, we kept running over. This year, I'm just going to cut people off completely. Sound good? Yeah.
So it's 20 with questions if there's 3.
If there's 3, yeah, 20 with questions. I'll give everyone a full 20 minutes. I will cut off extra questions, though, in case it's running over, just to make sure everyone gets a chance to speak.
So the questions are included in the 20 or not?
Not included.
Okay.
So we have 75 minutes total, so 20 minutes plus 5 for questions.
Okay. And then is the order the same as what's in the spreadsheet?
It actually does not have to be. If folks want to kind of communicate to figure out what order they want to go in, please feel free. It makes no difference which order it is. One more thing for these presentations, I would like everybody to come to class and also to make sure you ask a question or two throughout the entire presentation period. We probably don't have any way for everybody to ask questions on each talk, but make sure you do contribute by asking one of these questions. And if nobody shows up, I'll have to go to extreme measures like take attendance, which I hope I don't have to do. Cool. Does that sound good for everybody? Great. I found these really good last year, by the way, so I actually learned a lot. People picked really interesting papers that I was not super familiar with. So this part of the course, I think, is going to be super interesting for all of us. OK, so the plan for today is to basically talk about generative models. And we're really kind of focusing more on images than anything else. But of course, many of these ideas, they also apply to lots of other data modalities. Now, one thing to note is we've really been talking about generative models more or less this whole class. But they were kind of very restricted to token sequences, right? And the kind of objects that we're going to model with these generative models can be a little bit different, more complex in some ways, less complex in some other ways. So we'll spend a few minutes just on the basic idea for generative models as a whole. We'll talk about what makes this kind of hard, like what's the complexity of it. We'll talk about sort of the major approaches for image generative models. And we'll give some intuition on kind of how you build these and why they are the way that they are. Then we're going to talk about 3 techniques that all have kind of different pros and cons, and that have been all proposed and gotten popular at some point in the last 10 years. These are going to be normalizing flows, GANs, and then we'll finish up with diffusion models, which are kind of the most popular current technique for image generation. So we'll try to make sure that we understand kind of the differences between these things and what their real advantages and motivation are. Any questions about the roadmap? Hopefully everyone's heard of these things, and we'll have some insights into why they work the way they do. OK, so let's start with the first part. We're just going to talk through some of the basic kind of high-level ideas for generative models. The goal is exactly what it sounds like, and it's also what we've been doing. We're going to get a bunch of samples from some data distribution, P data. We observe x1, x2 through xn, and we want to approximate p data in some way. And then we're going to have some requirements. Specifically, we're going to want to sample, and we want to do this efficiently. And sometimes we'll want to be able to compute the probability of a particular x, ideally also efficiently. But that's basically the game plan here. These x's really could be anything. This distribution can be simple or incredibly complex. Most of the time, this p data of x is some process in nature. It's not some pre-existing distribution. It's something that actually happens in reality. And we have no direct access to what the distribution looks like. All we can do is interact with it through these samples. OK, now we've already kind of done this, if you think about it. Our p data of x here was the distribution of text, right, of language. And all of these samples for us were token sequences coming from our large corpora. And when we trained models like GPT, any of the flavors of it, we were doing generative modeling. Everybody agree with that? So in those cases, we even could compute things like p of token conditioned on previous tokens in the sequence. And we could sample. And in fact, autoregressive generation was all about kind of crafting new samples of this type. So really, we've seen these ideas. We're just going to make them a little bit more general currently. Also, this stuff doesn't have to be very complex, kind of rich objects. You can also be talking about really simple one-dimensional distributions. Same idea in that case as well. And kind of the very first approach to building generative models is literally building a histogram like this, right? And you smooth this guy, and then it's pretty easy to go compute a probability or get a new sample. So it can be very simple. It can be very complicated. It's just a function of what this data we're looking at looks like. OK, so the two goals that we talked about are, one, we want to do something called inference. This is a horrible use of this term. Inference here means computing the probability p of x. It doesn't mean generating a new x, which is ironically how we use the term inference, right, when we were doing GPT and other kind of transformer-based generative models. So it's horrible that this term is so overloaded. Just be careful with it. In fact, this term is used for more than just saying, hey, what's p of x? You often have more complicated things, like what's p of x given some conditions and things like that. Those are all called inference in probability theory itself. So don't get too confused about this term. The other thing we want to do is to sample, right? If I've already modeled p of x, if I have some approximate version of it, one thing I might want to do is to sample some new sample from it. And of course, I can combine these two things. I may want to sample from a conditional version of p of x. And in fact, we do that with prompting, for example, for language models, right? In that case, we're conditioning on the prompt itself, and we're saying we should draw a new sample from the generative model conditioned on that prompt token sequence. OK, everybody OK with this? So basically, the message here is I'm not saying anything that's actually new. We're going to do exactly what we've been doing, but we're not going to be tied to kind of the token sequence language setting. We're now going to be a bit more general, and then we'll look at images in particular. OK, what's the difference between tokens and images? Yeah?
Images aren't really discrete in the sense tokens are?
Yeah, exactly. That's a very big difference, and it's going to affect the way that we do things. An image, if you think of it as like a pixel array, it's this insanely kind of high-dimensional continuous object. And our token sequences were discrete distributions, right, over a vocabulary. It might be a pretty big vocabulary. It might be a long sequence, but fundamentally, it's a little bit different. Everybody agree with that? So that's going to be one sort of thing that we have to deal with. And as a result, we're going to have to be very careful about efficiency. Now, we can actually do things like run language model style models over images. We could treat pixels as tokens or characters, right? And then we could do things like create RNNs in pixel space. If we do this, it's going to get very complex and very expensive because images are really, really big, right? Even a pretty small image is a multi-million dimensional object. So this is where we're going to have to be a little bit more careful about what kind of models we build here. OK, so what is the biggest issue that we're going to kind of hit once we start doing modeling this p data of x? A probability function like p of x, right? It's a function. How do we model functions in general? Like if I tell you here's a g of x and here's some samples of it, how would you model it, not knowing anything else?
Assume a prior function.
I mean, that's actually a very reasonable thing to do. But I mean, the one thing that we always do in this class is we say, let's approximate it with a neural network, right? So what's different between P of x here and some just generic G of x, some general function that we can address with a neural network? Well, what are the requirements for P of x if it's a probability function?
0 and 1.
Yeah, it's got some constraints, right? It can't be negative. It can't be more than 1. And there's an even worse thing about it.
Has to all sum to 1.
Yeah, exactly. If you integrate it over your sample space, then you actually have to get to 1. So it's constrained in a way that's not sort of trivial to deal with, and that's the one thing that will make this actually surprisingly challenging. It sounds silly, but this is kind of the big issue. If we go ahead and apply the most straightforward idea, we're going to run into this problem. So what should be the simplest thing we do? If we just go ahead and treat this guy as some generic G of x, draw some samples from it, we can say, hey, let's set up a neural network. Let's parameterize it by some parameters theta. And let's go ahead and train. And the most standard approach to training is to say, let's pick this parameter theta in such a way that the resulting function maximizes the likelihood of seeing these samples. This is just maximum likelihood estimation. Everybody agree? And to put it in a very simple form, rather than just going ahead and kind of multiplying the probabilities of all those samples under the parameter theta, let's do the log version. Then taking log, it becomes the sum of the logs of p theta for each of our samples xi that we observed. And we're going to maximize this log likelihood in terms of the parameter theta, which is parameterizing our p theta function here. Everybody agree? This is kind of the most straightforward thing that you would do. And of course, if you know something special about p theta, you know it's a Gaussian, et cetera, then you can plug that into here, and you'll get to a really nice and often pretty simple estimation method. If you're drawing these samples from some real-life process, then you can't really make that assumption, and you have to find some very general form for p theta here. That's where neural networks are going to come in. Everybody agree?
What do you mean by a very general form?
Well, I don't know anything about what this distribution might look like, right? In that case, I want to be able to express any possible kind of distribution. Now, neural networks are nice because they're very expressive, right? Even simple ones, under some conditions, can express any function you'd like. So I need that kind of flexibility. Now, on the other hand, if I know some information, something special about p data, maybe I don't need the flexibility, in which case I can make the problem a bit easier for myself. Good question. Any more questions about what we're trying here? And what are going to be these challenges that we just talked about if I do this? Well, one thing is, if I go ahead and perform this optimization, I have to make sure that whatever I'm doing over here, this p theta remains a probability function. And even once I do this, how do I do inference over here? In other words, and I shouldn't say inference, how do I do sampling, right? Like suppose I've trained some neural network that somehow represents p theta of x. Great. How would I sample from it? That's actually not trivial, right? If I just get a function that when I plug in x, I get its probability density, it doesn't necessarily mean that I can easily draw a sample from this kind of thing. So somehow both training and inference / sampling here are going to have some challenges. Okay, so let's go ahead and try to deal with the first problem, the training issue. And let's try to separate sort of all these different properties of probability functions that we said we're going to need to deal with. And I'm going to express kind of p theta of x in the following way. It's very trivial, but it solves some problems, right? We first said, look, we need our probability function for any x input to it to be between 0 and 1. But of course, some general neural network isn't constrained to be between 0 and 1. It can have negative values, it can have very large values, and so forth. So let's say instead, we're going to permit f theta of x to be a function that has any possible continuous valued outputs, and we're going to pass it through exp. That's going to take care of the negative problem, right? Now, exp of f theta of x is greater than or equal to 0. Strictly, it's greater than 0, but anyway. I still need all of these guys to sum up to 1, so I'm also going to normalize by this 1 over z here. And by doing these two things, I've gotten everything I want, non-negativity, and I'm going to sum up to 1 / integrate to 1. By the way, this f here has a special name. It's called the energy function. This is a term that comes from physics, and that's why it has energy in it, but it's been used for this too. Okay, everybody agree with this?
So Z is a constant?
Z is a constant in x, but it is not a constant in theta. So let's take a quick look at Z, because you're on the right track here. Well, what I want from Z is that when I go ahead and integrate p theta of x over x, I want to make sure I get 1. So therefore, I can move Z over here, and I can say, okay, when I integrate this guy, I should get 1. So therefore, Z theta, for some fixed theta, is equal to the integral of this stuff here, x of f theta of x. This just says, hey, for a particular parameter theta I've chosen, I now have some energy function. And when I integrate x of the energy function over all my points, I'll get some value. I better divide by that value to make sure that I get 1. Okay, it's slightly subtle, but everybody agree with what the Z is? The Z just ensures that this p theta of x, when I integrate over all the x's, gives me 1. How did I set it? Literally, so that when I get this, it will give me 1. Everybody agree? Okay. So how easy is it in general to compute something like this? If I give you a theta, and therefore I give you some f theta, which is this energy function, can you compute this kind of thing? Who thinks the answer is yes, and who thinks the answer is no?
I can't.
You can infer that it's no pretty easily, right? Integrals generally are quite intractable, right? That's the hard part here. And this kind of leads into a bunch of training problems, right? Because, well, what are we going to do when we do maximum likelihood estimation? We're going to see some sample, and we're going to say, hey, adjust this theta to increase the likelihood of that sample, because I saw that sample in training. Right? That's literally what maximum likelihood is doing. It's saying, hey, I observed this sample. Let me change my theta, my parameters, so that this sample becomes more likely, because I saw it. And in fact, if there's a cluster of nearby samples, then I'm probably going to increase theta a lot in that area, because there's a bunch of samples, and I think there's a lot of probability mass over there. So what this means is I'll set theta so that f theta of x in that region is big. But if I do this, then I have to change my z as well, right? Because z is also a function of theta, and I've modified theta now. And this is really hard, right? So I need to recompute this integral, which doing even once is difficult, at every single step of training. So this is not at all straightforward. And in fact, I literally cannot train this way unless I do something to deal with this partition function problem. Everybody agree with this? Yeah.
Why do we call it a partition function?
Unfortunately, this is also coming from statistical physics, where there's a reason why it's called that. Yeah, it's rough. We need a class that's entirely on like the origins of various terms. Like, for example, why are they called eigenvalues? And the answer to that one is because it's from German, and eigen means self, and there's a reason for that. But yeah, all of these ideas are coming from these guys who basically said, I'd like to study small particles and the way that they sort of jointly move together. And it's very difficult to do that by just kind of tracing out the dynamics of every single particle, because there's like billions of them and they interact. So those people said, let's use statistics for this, and let's see on average what these particles do. And they introduced a bunch of these tools to help them, but they have really weird sort of notation and names, and now we're stuck with those because we inherited them. Okay, everybody okay with this? Okay, let me ask you another question. What is an instance of f theta of x where you actually know what z is? Maybe a very simple version.
Like a log thing?
Well, yeah, but I mean, that's too simple. One that leads to like a meaningful distribution. No, I mean, actually a log is fine, but yeah. Yeah,
Are you asking for like a setting of?
yes.
Well, in discrete tokens, you can like sum of the value over all.
Yes, you can compute it. But even in some kind of nice continuous cases, you can deal with it. Let's suppose my f theta of x here is the norm of mu minus x squared. What would this look like then? The distance, right? It becomes a Gaussian. And incidentally, you actually know what the z is for a Gaussian because someone computed the integral. What is it for a Gaussian? 1 over the square root of 2 times the, you guys know what I'm talking about, right? Okay. So there are cases where indeed we know what this is. And we're fortunate that in some of those cases, it's a closed form expression in terms of theta. So then it's easy to compute. And then, in fact, I can train. There's no problem. The troublesome part is I will have to restrict myself to very special functions f that maybe don't fit my data all that well. So really, I'm going to have to deal with something else potentially here. Everybody agree? Cool. OK, so let's see different ways of getting around this partition function. As I mentioned, pretty much every generative modeling method has to be able to do this. One thing we can do is to say, hey, let's give up on the whole idea. Instead of directly modeling p theta of x, where p is the PDF, then maybe I can just not do that at all. Now, if I can't do that, then the whole inference, the whole computing the probability thing, I can't do it, right? But maybe that's OK. Maybe I can still sample. So what's a type of generative model of this form where we sort of completely given up on at least explicitly getting the PDF, but we can still draw really high-quality samples? Yeah, again, right? So again doesn't actually try to directly get P. It doesn't train with maximum likelihood at all. It just says, OK, we're going to create a network that's actually really good at creating samples, but it has nothing to do and no ability to directly compute P of x. And the way we're going to do it is from some alternative means of training, not maximum likelihood, because we have no likelihood. It's going to be through adversarial training. And we'll talk about this, but does everyone kind of get the idea there? Cool. OK, so one other way we could do it is the thing that we said. We can choose some special choices of either our p theta or our energy function f theta that makes z still tractable. And we'll see some kind of nice ways of doing this, but we are more inflexible, and that's a downside. Another thing we can do is to say, OK, maybe z computing it exactly is impossible. Let's come up with some approximations that are tractable. We do that all the time anyway. And there's different techniques that basically let you do essentially this. If you've heard of VAEs, they're doing this, variational autoencoders. And finally, we can come up with sort of alternative training that also does not really directly do maximum likelihood. I mean, we talked about GANs, but we can also do these score-based diffusion models that still have a P in there, but we're not interacting with it in a certain way. And this is kind of going to be where we go to, and this is really the reason why diffusion models are so powerful. So we have a bunch of different sort of ways of getting around the big problem, all of them with pros and cons. Now, let's actually see what these look like. I borrowed this slide from Lillian Wing's blog, which is really nice, so you guys should check out the blog as well. This is kind of telling you the structure, in other words, kind of the block diagram, the architecture, of all of the approaches that we talked about. And besides the name, it's also telling you the way you're going to do training for these. Everybody OK with the setup here? Cool. So let's take a look at some of these. So here's what's going on for GANs. Notice that there's no P anywhere, right? So here there's a P. Here there's almost a P. We'll talk about that. But here we're not doing anything to do with the probability, right? We're just saying, let's train a function called G, literally a generator. You plug in whatever you want. It can even be noise over here. That's Z. And it gives you some sample x prime that should look like it's from the real data distribution. And how do we ensure that we can make it look that way? Well, at the same time, we're going to get this discriminator object. This thing is trying to say, hey, can you make sure that this x prime and x are distinguishable? And we're going to try to trick this guy. We're going to say, let's make this generator so good that this discriminator cannot tell the difference between real samples and these fake ones that we've created, these synthesized ones x prime. So if we have a good discriminator, and we build our generator in such a way that it can fool this good discriminator, then our samples must be good as well. They must be realistic. Everybody agree with the idea? Now, making sure that we have a good discriminator is the other problem, right? So essentially what we'll do here is try to play off these two things against each other. We'll try to make our generator better to fool the discriminator. We'll try to make our discriminator better after that to figure out that indeed these samples are generated, and so forth. But again, the major distinction here is we didn't really ever deal with P of x. We did not ever try to say, OK, let's maximize the likelihood of the observed samples. And therefore, there was no partition function anywhere. So we just didn't deal with that whole issue. Any questions about GANs, just at high level? Now, one thing that's going to be annoying here, and there's going to be a trade-off, of course, is that making training for these parts stable, adversarial training, can be hard. going to be very easy for our learning to just kind of collapse. So we have this nice benefit, but we also have a cost. Cool. Now let's look at some other versions here. These two guys over here, and really all three of them, are going to be a little bit different. We are not explicitly now going to train a generator. Instead, what we're going to say is something like the following. Let's take our original data. Let's encode it into some latent space over here. We did this, right? Remember our encoder-decoder models? That's literally what we are doing. We're going to do it a slightly different way. But then we're also going to simultaneously get a decoder that takes you from the latent space back to the original space here. And therefore, if I've trained this network, I can sample by saying pick out some z, again from any distribution, plug it through my decoder, and see what I got on the other end. Everybody agree? Okay, now how should I train this thing? For autoencoders and generally, what you really want here is to make sure that if I pass an x through, I compress it into this latent space, I can recover it at the other end. So training is literally reconstruction. Okay, now how do I avoid a situation where these pieces are trivial? If I'm saying, hey, my training process says plug in x and recover x, why wouldn't this just all learn the identity function?
Compressing it and see.
Yeah, exactly. I can make it in a much lower dimensional space. I can also add noise. I can do a bunch of tricks that forces this to be different. And therefore, reconstruction actually is meaningful. It's really training this. Okay, everybody agree with that? Okay, now this we can do with maximum likelihood. Unfortunately, the challenge is, again, the partition function. There's a special training method that we won't talk about too much, these variational lower bounds that get us around that. Okay, now this is all about taking a point and coding it to another point. Let's do a similar version that's called flow-based. In this case, what we're going to do is not train this encoder to take this point to a latent space version. We're going to say, hey, let's consider the original data distribution, whatever it is, some complicated thing. Let's repeatedly transform it until we have a distribution over the latent space that is really simple. What would be a very simple distribution that we'd like to deal with here? Yeah, like a multivariate Gaussian would be nice, right? That's a very simple distribution with good properties. So we'll want to build a chain of transformations that take in the input distribution, modify it until it becomes a multivariate Gaussian. And now I'll need one more thing, reversibility. Whatever chain of transformation got me here, I want to inverse it so I can recover the original space, the original distribution. And if I do this once again, I have this very simple idea. Go ahead and pick some sample here. It's very easy and cheap to sample from a Gaussian distribution. Run it through this inverse chain of transformations, and I'll get back a point that's in the real distribution. Everybody okay with this one? Now, what's the downside here?
Functions have to be invertible.
Yeah, exactly. I can't do any old transformations I want because if they're not invertible, I can't undo the process, and therefore I can't do anything. So I'm limited to particular kinds of transformations inside here, and that's another downside. Okay, let's talk about our last one, which is going to be kind of where we head to. This is the diffusion model. There's many variants, but this is kind of the most standardized one. Notice that what we're doing here is not like a single flow per se, taking me to some particular latent space for z. What we're going to do is simply gradually add noise to the original image. So we're going to be sticking to the same space, still pixel space for the image. But we start adding noise little by little by little until we've gotten to a point where we're completely noisy. There's no structure left. The original distribution is basically melted away, and I'm back to a distribution of noise, but on the original data space. Okay, now then again, I can sample something from this noise distribution, which might be Gaussian. Then I can reverse this process, remove noise. And by doing that, I'll get back to a sample from the original distribution. Not too different from here, but there's not as clean of a distinction of like, here's the latent space, right? The spaces are really the same, you're just adding noise. And you're adding it in small amounts, little by little, until you get fully noised, and then you undo at the sample. Okay, everybody agree with kind of these mechanisms? We'll talk about them in a bit more detail. Any questions? Yeah.
Assuming we're going to go into like how do you remove noise? Like you can't just wave your magic wand and noise be gone.
That is actually the thing that we're going to train. We are going to craft deep neural networks that are capable of doing the removal of the noise.
Right.
But yes.
And that
Yes.
on how those parameters.
Yes, but it's easier. For adding the noise, I can literally say, here's a distribution, which is the noise distribution, that I add to this sample. And I'll control the noise parameters there. How big is the covariance, etc. Then I'll do another one here, and then another one here, and so forth. What I get to pick is how many steps I do, and exactly what those noise parameters are going to be. So here, I don't really need to learn that part. I can do things like learn the schedule and stuff like that, but that's not critical. The denoising part is the hard part. There, I need to parameterize it and learn it. Yeah.
For the flow-based models, so you said they're restricted by functions that are invertible. So do they have to be exactly invertible, or can we use some approximation?
You can try, yeah. Unfortunately, it gets a little bit more ugly if you do that, but yeah, you can do that too.
Because in diffusion models also the forward process is,
Yes.
but the reverse
If-
inverse process is.
If you'd like, this is really like a very special case of this, but sure. We're going to distinguish it here just for this reason. Cool. More questions? All right, let's talk about intuitions, and then we'll take a quick break, and you can ask more questions. This is sort of my intuition in general. Whenever I think of, here's a new generative model, what is it trying to do? And of course, you can look at these block diagrams, but it's just useful to keep a few things in mind. One thing to think about this is sort of distribution interpretation. We really want to take some simple fake distribution and map it into the complex real data distribution that we care about. Now, this mapping can be done in many different ways, but really this is what we're trying to do. And the underlying motivation for this is the simple one, that it's very, very easy to deal with the simple distribution. It's convenient and efficient to draw samples from it, for example. And then if I have this learned map, I can just go ahead and undo that, basically. Go ahead and get real samples from the actual distribution. So this mapping principle kind of applies to a bunch of the pieces that we've seen here. It also leads to this latent space interpretation, where you might be thinking of, well, you know, real data lives in some much lower dimensional manifold that's inside this larger overall space. Think of images, right? When you think of an image of 1,000 by 1,000 pixels, that's a 1 million dimensional object. But if you think of all the possible things that live in that 1 million dimensional space, very few of them make up real images, right? The real images live on this sort of much, much smaller manifold inside. So one thing I could think of is, can I map that manifold to this lower dimensional latent space where every point actually means something? Does everybody kind of see what I mean by that? And if every point means something and has some realistic associated picture, I just need this reverse map that gives me that associated picture that is on the manifold. Okay, it takes a little bit of time of thinking through that stuff. Okay, and the other sort of interpretation, but it's very related, is, well, to learn what's going on in a distribution, I kind of mess with it in some way, and I figure out if my model can undo the way I messed with it. And we've been talking about this already, right? We talked about self-supervised learning. All of those examples from early on in the class, we said, hey, let's angle this image, and let's teach the model how to, remove the fact that it was angled. Let's, color out some part of the image and force the model to recover that part. Right? So we're essentially teaching the model what matters, teaching it what the distribution is like. That's basically what we're talking about here. I can capture a distribution if I can mess with it in some way and convince my model that it's capable of undoing that mess. Everybody okay with this kind of second intuition too? And this one's sort of directly usable for the diffusion models, right? I'm adding noise at various scales on different schedules, and I need to train my model to be able to undo all that stuff. If it can do that, then it knows a lot about the distribution it's trying to capture. So it makes sense that I can sample from it. Cool. Any questions? Okay, awesome. So basically, if you take these two intuitions and you kind of combine them with these training considerations that we just talked about, that really gives you all these different approaches. There's one more annoying thing that you kind of have to care about. All of these approaches can get you to very, very good, high-quality samples. If we're talking about images, we're talking about photorealistic samples. But it really depends on how much data you have to train on and how kind of complicated training is. So if you actually limit yourself in terms of how much budget you have for compute, these different methods have sort of different quality outputs. So for example, the flow-based methods are really nice from a theoretical point of view, but usually for some amount of compute, it's not the best technique, as much as it's nicer. Diffusion models are popular because even for a fixed amount of compute, they're actually really good. Now, GANs are really good because sampling is incredibly cheap. You literally run a point through your generator, but they're very hard to train. So you have to kind of trade off all these considerations against each other to figure out what's the best technique. And as a result, we've kind of stuck with diffusion models for the most part for kind of what we do generative modeling with images. And not just images, people are working on this for actual text as well, which should get very interesting. OK, let's take a break there. You guys feel free to relax for a minute, or you can ask more questions. Yeah?
How does the text version of diffusion work?
It's complicated because you have to figure out what noise means. You have to figure out like what exact space you want for these objects. And you have to approximate what the continuous version looks like, which is more annoying. So no one's gotten it to fully work to the extent of a transformer-based model, but that's sort of what people are looking at.
Is the promise of a diffusion-based text model that you can generate multiple tokens simultaneously?
You can do a lot simultaneously, yeah.
Okay.
But the other thing that we want here is kind of going away from all of the annoying aspect of transformer-based language models to something that's sort of cheaper and easier.
I guess, do you have an example of what that would be?
No, not really, right? I mean, the technique for training is now so different, in fact, also for sampling,
Right.
that you're going to get something very different. But I don't know how to compare it like one for one here.
Fair.
Sure.
Yes, so you were talking about mapping the simple distribution into a complex distribution.
Yep.
And learning that map.
Yep.
Does optimal transport come into picture?
No, because it's inefficient in terms of what we want to do there. But yes, I mean, the idea is not that different, right? You are talking about two distributions related through a particular function. You could use optimal transport. The annoying part is the actual doing the optimal transport. It's going to be difficult to go ahead and do that, right?
Because of the like dimensions of the distribution that you're talking about?
Yeah, exactly. Yeah, so think of what you need to do, right, to go ahead and compute optimal transport. It's computationally expensive for what we want here, unfortunately. You can do it, but it's not what we'll typically do. Instead, we'll kind of parameterize like the chain inside the flow in some really simple ways and train on that. But that's a good idea. I mean, I like what you're thinking of. Yeah.
Is there a point to like GAN-style adversarial training for diffusion models, where you just kind of replace the generator with a more complicated generator?
People want to do these kinds of hybrids. I've never seen one where it's like people got excited and wanted to use it for everything. But what you're suggesting, like, yeah, there's interest in doing things like that. We're going to run into the same issues, though, of like, how do you trade off like how hard training is and like how much you compute you want to throw at it versus like the quality of the samples you get. Yeah, let me know. If you email me, I can send you some papers I've seen about these hybrids. It is interesting in any case. Cool. Yep.
How do you know when to stop adding noise? I mean, if you keep adding noise, eventually you're going to destroy all the information. And
That's what you want to do.
basically recover it.
No, that's good, right? Like,
It's just that you're training like at each step.
yes,
Sort of
exactly.
that you can go from here to here, and
Yep.
then when you add the whole cascade, you can give it just
That's it, yeah.
garbage and it'll produce something.
Yes.
Okay.
Yeah, so what you're describing is exactly what generative modeling is. It's taking garbage, undoing it until you get back a real thing. But you want to be in the full garbage setting, right? If there's any structure that's left over, it's very difficult to deal with that distribution, right? That's like the thing we're trying to avoid. But you're right, like how many steps is a hyperparameter? And that depends on like the setup you do. It could be long. Like for some of the models we'll talk about, it can be thousands of steps, which is not super great. That's actually the bigger inefficiency of diffusion models. And yeah, that's the one annoying part.
Getting the
Yeah, sorry.
Oh, I was just, so, I also had a question about, you kind of mentioned that formula with the exponent, and then at the bottom you have a constant that you.
Yeah, the partition function, yep.
Yeah, isn't the partition function kind of like a Boltzmann distribution?
What kind of distribution?
A Boltzmann distribution?
No, that's a general thing for any distribution you'd like, right? Basically, if you represent your distribution as some unconstrained function, right, then you have to normalize. And this is true for literally anything you want here.
Fair, yeah.
Yep. Now, sure, okay, if you set up prior over distributions, then z itself can become a random variable of its own distribution. I think that's what you're referring to, but yeah.
Okay, and then wouldn't, like, I guess, is there a study on what the role of the exponent is? Because you could also normalize
You can.
in some other way, right?
Yeah.
But I would assume it would result in sharper peaks, or you could get sharper peaks.
Correct, yeah.
Wouldn't you want that?
In general, no. It basically turns out that doing x of a function that's parameterized by theta, that falls into this big family of things that are called exponential families. And many of the distributions we work with are exponential families. And so Gaussians are, exponential RVs are, many more. They have many really amazing properties. And they're always nicer both to kind of estimate and to sample from and everything else. The kind of big thing there is they have this property that's called maximum uncertainty or maximum entropy. Basically, if I give you the moments of the distribution, so you don't know anything except the mean, the variance, higher order moments also, then this particular form, this exponential family, these are the ones that have the maximum level of uncertainty, the biggest spread of probability mass. So they're also very conservative in that case, right? You're assuming less. So yeah, there's like a million good reasons why that's an X but not something else, but you're right, you could do other things as well.
So you are kind of trying to get very narrow, sharp.
Yep. Yeah, I mean, if you're studying distributions that have polynomial instead of exponential tails, then you're going to do something different there, right? And that's very common as well.
My question would be, I think these generating models all learn different representation space. And how do we...
Well, sometimes they don't have a representation space, right? Like the diffusion models, we really didn't. It was just the original space, but with noise, right?
Yeah. But my question would be I think the representation is somehow related to a task you design, or the
Yes.
data set you choose.
Yes.
How do we know which representation space would be better for other tasks, or when we concatenate different paths into a model?
We don't, essentially, right? These are all different techniques. We can take our samples from our data distribution, and we can say, let's train one of these generative models. Let's sample from it. Let's introduce some metric that says, here's how good the samples are. And let's say, well, it looks good on this metric, or it looks bad. We don't know a priori, though. We cannot say anything.
Totally empirical thing, or
Yes. Yeah. Sometimes you can prove something theoretically. You can show one of these models is expressive enough for some distribution. The problem is it's almost never useful in reality because I don't know any properties of my true data distribution, right?
Yeah, I agree with that. Is there any way to hybrid different representation space
Yes.
for different tasks?
Yeah, of course. I mean, all these things, I could put together a bunch of different models. I could merge them. I could do things like that. But it's still empirical, right? There's no, there's no thing that says this is the correct architecture to combine some of these things. But I wouldn't, don't stick to the representation space version of things too much here. For a long time, people have had this goal of well, let's try to figure out a nice disentangled representation space where every component of the latent vector means something meaningful for my data, right? Like the size of the objects, the color, whatever. It hasn't really worked. So yeah, that's the hard part there.
Do you think information theory stuff will be more fundamental to think all these kind of things?
All these things are fully compatible with information theory. You can draw rate distortion curves. You can do everything. Information theory here is a tool that can characterize these things. It doesn't tell you what's a new model that you should use, though. That's the hard part for it. All right, lots of great questions. So we don't run out of time. Let's move on to talking about normalizing flows and GANs for a little bit, and then we'll finish off with diffusion models. Okay, so let's jump into these flow models. This is the thing we talked about, right? We still want to do p theta of x, and we said the annoying thing for us was really, well, we don't want to compute that partition function. So we don't, strictly speaking, necessarily want to do maximum likelihood. But basically what we're going to really do here is want a good fit for the data. We still want to be able to compute this p theta of x. And most importantly for us, the thing that we ultimately care about is we want to be able to efficiently draw samples. And in this case, we really are going to have this latent vector, this latent representation. So let's go ahead and do that. Rather than modeling p theta of x, maybe we can work with stuff that's happening in this latent space z. And then we'll bypass this whole business of the partition function and so forth. So the architecture that we're going to do here is the one that we talked about. We're going to say, hey, let's pass x, the distribution from the original data, through these transformations that are ultimately going to take us into a simple distribution over z, like a Gaussian. And then, if we want to sample, we'll just go ahead and sample a Gaussian, some other z here, and pass it through the inverse until we get back to the original distribution. All right, everybody agree with the idea? Cool. Okay, so what's going on here? We're basically going to say, let's use a chain of these transformations. It's not going to be just a single one here. And this chain, it's going to say, okay, let's start from our distribution over z, which is over here. This thing is simple. It's a Gaussian. Now, in principle, it's going to be a higher dimensional Gaussian, of course, but let's just pretend, for simplicity of drawing, that it's just a univariate Gaussian. And then what I can do here is draw some sample z0 from this space. Let's call it p0 of z0. This is just a simple distribution over the latent space, and I can draw a sample from it in a very easy way. This is what this part looks like, and now I'm going to start applying these functions. These functions, of course, you plug in a particular point, and you get back another point, but the main thing we care about is what their effect is on the whole distribution. And we're going to pass this distribution through the function f1, get some new distribution. We're going to then pass that through some function f2, get a new distribution, and so forth. Over here, I'm passing through fi. This is the ith function in my chain of transformation functions. And when I do that, I'm going to get back some new distribution. Notice that it's getting more complex, right? Here's a distribution that's not unimodal. It has multiple peaks. It looks complicated. I cannot express this just with a Gaussian by itself, right? And I keep doing this until I get to the very end. I have some number of transformations, this capital K, and now I have a data distribution that really is the original space that we're talking about. It's very complicated. Everybody agree with this logic? So this is the process of sampling. If I've trained these transformations, all I have to do is do a cheap sample in this very simple distribution. I apply these transformations, f1, f2, up to fk, and now I get a point, which is a sample from the original data distribution space. Okay, everybody agree with this idea? So sampling is relatively simple here. What is going to be more complicated for us to deal with? Yeah, we've got to train these guys, right? If these f's are not anything that has to do with my data, then whatever I get at the output here is not going to match the original data distribution at all. So I have to be careful, and I have to train in a way that I can actually match this guy. Okay, everybody okay with that? Cool. Okay, so for this part, so this is the sampling, by the way. It's exactly what we talked about. You just sample from the latent space z, and you apply these transformations. Let's talk about the actual training process. We'll need a little bit of stuff from probability theory here. Does everybody know kind of what to do when you want to change variables for a distribution? Okay, if you forgot, that's okay, but I mean, this is just calculus-free kind of stuff, right? What happens if I apply these transformations to the density? Well, the distribution doesn't really change, it's just kind of reparametrized, right? So let's suppose that I write that z, my latent, is f theta of x. Then I can say, okay, well, what happens to the distribution over x, and what happens to the distribution over z in this case? Well, I must have something like this, right? The distributions have to match up because I'm just passing it for some transformation. Well, conveniently, then I can write this really simple expression where essentially I can write everything with the z notation, but I have to have this additional determinant of the Jacobian term. This is just basically what happens to a transformation when you pass it, what happens to a distribution when you pass it through a transformation. Okay, so nothing special is happening. We just wrote down an expression that comes from like, calc 3 or probability 1 or whatever. But the good thing is we can use this for training. Let's see what we mean by that. Well, we're going to run exactly the procedure that we talked about before. This procedure is just maximum likelihood. We want to maximize over theta the log likelihood of our data set. That is the sum over all the data points of log of the likelihood, p theta. We said doing this directly has that problem that we talked about before. So let's go ahead and replace x here with this latent space that we've been talking about, z. That expression from the previous slide, I can plug it into here. Okay? So now, instead of log p theta, I have log pz of f theta. Right? This is the distribution over z's. And I have this additional term that I have to pass through the log in front. And this is just a log of the determinant of the Jacobian. Now, this is nothing too scary. I've now expressed everything in terms of this simpler distribution, plus this sort of correction term that looks at how these different variables interplay. Right? So now I have something that's sitting inside the z version, and I have something here that adjusts for writing things in terms of z. Okay, so I have kind of a loss function, but it has two parts. Something that's taking place in the latent variable space, which if I have a simple distribution, I don't have to deal with any problems with it. And I also have to deal with this determinant of the Jacobian matrix. And maybe if I pick my f's in some reasonable way, this term is actually something I can train over as well. Everybody okay with this? Trace out the math for yourself. It's just some basic calculus. It's nothing too scary. is just telling us, hey, we can go ahead and move into a nice space where the scarier things about directly training with maximum likelihood are not as scary. Okay, so what can we do? We have to pick out these f's over here. Right now, we wrote it with just one single f, right? A single transformation. We were talking about chained transformations. So what I must do is to kind of figure out what that chain looks like. And that means I have to essentially pick out some transformations that are reasonable. Wait, real quick, let me show you an example of what's going on here. Here is the transformation in the middle. It's a little bit unintuitive at first, but just think of it as a function. The x-axis is literally taking one of these points from the x-axis here. These are the points our distribution is over. The y-axis is telling you what's happening to it. So over here at 0, you do nothing. You know, over here at 2, it becomes something there, etc. So when we pass this original distribution through this flow, through this transformation, I get back this distribution, which maybe not too surprisingly doesn't look super, super different from the original distribution. So this flow has really not done too much. And that shouldn't be shocking because if you're looking at it, it's kind of like a linear function, right? It's not doing too much here. So this is kind of an untrained version of the flow. Let's see if we can actually train it in a way that gives us a good distribution. What would be the distribution that I want to see on the right over here? Yeah, some Gaussian. I don't want to have these two peaks and so forth, right? I want to transform to this very simple distribution in the latent space. Okay, let's see it. Notice that now my flow has actually interesting stuff going on in there. It's got this weird bump over here. That's not too shocking because the bump lines up with where the two peaks are basically, right? So it's kind of been trained, it's taking into account the data, and what we're seeing here is not a perfect Gaussian yet, but getting there, right? Still reproducing some of the two peaks, but we're getting a lot closer to a Gaussian. Okay, everybody agree? So this is what the training process is trying to induce. Now, how would I reverse the process to sample? Just need these guys. Just flip it, right? Don't really have to do too much else here. Are these things invertible currently? They are, right? It's not like we're seeing, you know, points on the x-axis that have the same value, so we're okay. And this is getting a little bit flatter, but it's still moving up. So these are indeed invertible, and therefore all I have to do is to write down the inverses. I sample from this Gaussian, that's easy. I run it through the inverse, and I'll get back a point from there. So that's the whole game here. Everybody okay with this? Question? Okay. Okay, cool. So the only thing that's going to be annoying is rather than just have these really simple functions, I do have to figure out like what's kind of a reasonable set of transformations that one, when I chain them together, allow me to do this, and two, are invertible. Agree? Okay, so let's see some examples, right? One thing I could do is, you know, affine transformations. Take my variable x, maybe center it, apply a matrix, hopefully one that's invertible, so let's write down A inverse. If it's not invertible, again, we're in trouble, right? We can't undo the process and sample. Construe element-wise things, so rather than treating x1 for xd as a vector, I can apply some invertible transformations on each coordinate separately. I can use all kinds of splines, which are these sort of different curves that are connected by points. These things can be made to be invertible. These give you good nonlinear behaviors as well. So you've got a lot of really nice choices to make here. Again, we want it to be invertible, and we're also going to differentiate for these things, right? So ideally, we want it to be differentiable as well. Okay, awesome. So this is it for these flows. Very simple idea. They're not too inefficient. You do have some design choices that you have to make. The big sort of downside is the performance of these things isn't quite as good as diffusion models. That's why we're not using them. Or rather, we're not using them except for some specialized cases. Let's go ahead and talk about GANs now so we don't run out of time. The idea is what we've been talking about. We're going to drop this idea of modeling the density in any direct way. We're not going to model it through the latent either. We're just going to ignore it 100%. We're going to have a really clever idea, which is let's use the notion of a good sample as one that tricks somebody, that makes them think, wow, this is truly from the real distribution. And we're going to play a game here. By the way, this painting has been famously forged throughout art history a bunch of times. We're going to have this weird two-player game. We're going to have a forger that tries to trick, you know, let's say an investigator. And then the investigator wants to be really good and detect any forgeries. Now, if we have these two people play off against each other and get better and better, then eventually the forger is going to be our generative model, right? We can ask them to make photorealistic versions of whatever we want. Everybody agree with the idea? Okay, let's see the actual kind of setup. Well, let's go ahead and kind of pick these two objects, the discriminator and the generator. The process is going to be actually fairly similar to before. Let's take some z, which is random noise. Again, noise is really easy to sample from, so that's why we want this. Pass it for the generator, creates fake images. Then we have some real images. These are our samples. And we want to train this discriminator network that can distinguish between these two things. And if it gets really good at distinguishing fake from real, we'll say, okay, can I go ahead and make my generator better so it creates more realistic samples until this guy's being fooled? And then we keep this process going. Okay, does the intuition make sense for everyone? Cool. Okay, so let's see how this training is going to work. We're now going to split our parameters into two sets. One for the discriminator, theta d, and one for the generator, theta g. If we fix the generator, what is the job of the discriminator?
Classify the things that they generate.
Exactly, yeah. It's just a classifier that's literally saying for a particular sample, is it real or is it fake? And if it truly is a real sample, it should say it's real. And if it is a fake sample, generator from the generator, it should say it's fake. So it's just binary classification, right? It's a very simple kind of network. You can train a CNN to go ahead and do this. We can also write a simple expression for it, right? If we have some samples drawn from the true distribution, this p data over here, then what we want to do is to maximize theta in theta d, the parameters here. For the real data, let's make this as large as possible. These are the samples that came from over here. And then for fake data, which is some noise z, passed through the generator, which here it's fixed. We're not training it right now. When we plug this guy into d theta of d, we want to get 0. We want to say, hey, it's fake. So we want to maximize both these things. We want to say the real data should be classified correctly as real. The fake data should be classified correctly as fake. And we just go ahead and train this guy, gradient ascent, because it's a maximization problem. And that's it. Everybody agree? Okay, now we're going to have to actually deal with the generator as well, right? So we have to make it better until it can fool the discriminator. And that means we're now going to introduce a second layer for the optimization. Previously, we just said take this interior stuff over here, fix the generator, and try to make sure that this discriminator is as good as possible. Maximize this guy in theta d. But now let's take that whole thing and minimize it in theta g. This is saying, hey, I want my generator to be good enough that this discriminator is getting fooled even though it's trying as hard as possible to actually figure out which are the fake samples. So this is a mini-max game, kind of slightly more complicated optimization to perform, but these are the two components that we need, right? We want something that's as good as possible at detecting fake versus real. We want something that's as good as possible at forcing it to not be able to detect, and therefore creating a very high quality distribution. Does this sound good? Can you do this optimization in PyTorch? The answer is yes, but it's actually pretty hard, right? I mean, this thing is not that easy. Draw the picture for what these two components are doing, the min and the max, right? You're going to be sitting on some weird saddle and trying not to fall off. It's not super simple. So this is the really big problem here. The simplest way to train this kind of thing is to alternate these two things, right? So first say, okay, well, I want to say run gradient ascent, generator fixed, just make sure you do the maximization over theta d. And then we're going to do gradient descent, fix theta d, and make the generator better. Notice that this term over here, this is the real data term for the discriminator. It's not a function of the generator parameters. There's no theta g in here. So in this part, it doesn't show up. It's just this component. So alternate these two steps of training and hope nothing crashes and dies, which it often will. Everybody okay with this approach? Cool. Okay, so training is not very often stable. This is the real problem with GANs, and this is also why they've slightly lost popularity. There's lots of tricks here, even really simple and weird ones. Like for example, over here, instead of training log of 1 minus d, you replace that with log of d. directionally it's the same, right? You're now maximizing log of d instead of minimizing log of 1 minus d. Interestingly, this actually kind of helps with sort of the kind of the gradient landscape there. But still, this remains actually pretty difficult, unfortunately. Okay, one thing I haven't really talked about, which I'll sort of paper over, when I've been talking about, well, you know, use a deep neural network for G theta and things like that, there's also actual choices in terms of what architecture you should use here. You basically can do whatever you want. Well, for the discriminator, it's just an image classifier, so a CNN will work. For a generator, you have a lot of different approaches, but really, you can do all kinds of kind of nice networks. Here's a really simple one. Start with some 100-dimensional latent space vector. That's our noise vector that we plug in. You have almost a reverse CNN, right? It's going from this low-dimensional vector kind of back out, increasingly making these 3D volumes bigger and bigger, but thinner, until you get to a free-channel RGB image. So almost like a reverse version of CNNs. You can also do UNets and lots of other kinds of architectures here. Okay, I'll jump. These examples are unfortunately really old from when I initially made the slide. Modern GANs can produce extremely high quality, very large images that are truly high quality in the sense of being photorealistic. But even from the beginning, this is like 2016, a couple years after they came out, in not too much training, you start producing some very high quality images. And notice the thing that's really easy here. Once I've trained this guy, generating a sample is neural network inference. I plug in that 100-dimensional vector, get the output. That's it. It's not some complicated iterative process. It's something really simple and potentially very fast. That's one advantage, but the training here is the big disadvantage. Okay, any questions about GANs or even flows? Cool. Let's take 1 minute, and then I'll try to, yeah, we should be okay on time, finish up the diffusion model section. Any questions in the meantime? Yep.
What is exactly input for the GAN?
Well, the input to the discriminator or the generator? The input to the discriminator are images from our original data space. These are full images, basically, right? And there, the goal is to say, did this come from my actual data distribution, my actual samples, or from the generations, right? But either way, they're the same kind of images. Then for the generator, the input is this latent vector, which is just noise, usually lower dimensional. That's this 100-dimensional Z I just showed. I'll move it back up there. You take this thing as input. The output is just an image again, a synthesized one. Here's what I mean. Oops. This is just the architecture for the generator. I have some 100-dimensional vector over here. There's just noise in there. Pass it through this network. You generate a full image.
So the discriminate, I mean, when we're doing image classification, we can use CNNs, but this is a much more general process, right? I mean, I think
Yep. You can do this with text, for example, if you want to. It's even more challenging and unstable to do this. But yeah, for the discriminator, any neural network, or even more generally, any model whatsoever that can do binary classification and operates on your input is fine for that.
So for flow-based models,
Yep.
When we're trying to do a conditional generation, then do we have like
We have to attach something else to the latent space. We have to make sure that attachment can guide the choices from the latent space to push you towards something that when you do the reverse transformation, right, matches up whatever you condition on. So this is an actual issue. If you want to do text to image, you have to hook up one of these parts. We'll talk about it for the special diffusion model case. Cool. Any more questions?
So what is the issue with the instability? What caused that instability?
So the really big problem here is actually it's very easy for your generator to collapse until it only produces exactly one thing. And if that exactly one thing is very photorealistic, then the discriminator says, okay, great, right? It's real. Right? So then what do, right? Like you no longer cover your entire data distribution. You're now collapsing to one particular mode of it, right? How do you avoid this? You have to start finding some way to push your training process until you get more diversity out of it. But it's so easy for your training to crash into one of those modes. Of course, you also have the more general problems of the entire network could just diverge frequently unless you pick really good hyperparameters. So that's just a general issue of these things.
So for inference, I just apply the generator and
Yes.
Okay. So how do I control the direction of generation? Right?
You have to bring in a conditional version of the GAN.
Okay.
This conditional version now says something about the input that you're doing.
It's just like text or
It can be text, but it can be other things too. Traditionally, it's really just sort of other parts of images. You say, okay, well, even though my original P data has many different things in it, I can sort of pick out subsets of that have some meaning. And therefore, by doing this kind of conditional version of a GAN, I can push myself toward those regions. All right, let's talk about diffusion models. Okay, so basically we're going to get back to this kind of something that looks like a flow, with the exception being that once again our latents here are a little bit different, right? We don't have a single latent space with z being our latent vector. Really, all of these different guys, my x1, my x2, my x3, and so forth, all the way up to z here, even though they're in the original space, they're all kind of my latent variables, so to speak here. So this is kind of what's going on. It's kind of a very special version of a flow, but it turns out it's just very powerful. And it's a little bit tricky to talk about diffusion models generally. It's not like one specific approach. It's really a kind of a broad family of connected approaches. So I'll start by talking about a couple of them. There are others, and if you get really into this, you can kind of figure out exactly what the different connections are. Okay, so let's talk about a version which is very popular. It's one of the two sort of general popular approaches. This is called score-based generative models. Again, we're going to go back to this issue of the partition function. Same exact thing that motivated all these other approaches, normalizing flows, GANs, and so forth. So the trick we're going to use, as before, is not to directly model the PDF, but in this case, something very related to it. We're going to model this function called the score function. Notice that p of x, the PDF, is in there, which is confusing, right? Because it feels like we're still doing something with it. But the function is now something different. It's the gradient of the log of the density, but with respect to the data x. Okay, this is not super intuitive at first glance, so just look at it for a little bit. We're going to talk about the log of the density, but we don't care about the actual absolute values of it. What we really care about is the derivative of it with respect to the data. So when you think about this, what we're really talking about is kind of for any point, what are the directions that take me into another more popular region of the space versus what's not? That's what this object really is. Okay, is everybody okay with this thing just from a glance? Again, this is different from what we normally do, even though it looks very similar. Right? When we were talking about maximum likelihood, we said take log p theta of x and modify theta to make it more likely for our data, right? And therefore, we did things like take the gradient of log p theta of x, but with respect to theta. That is not what we're doing here. We're doing it with respect to the data x. Everybody see that distinction? Okay, that's the important thing here. So this function is called the score function. Again, it's a function of x in itself, right? Yeah, it looks weird, but it is a function of x. And this thing is called the score, the gradient of the log likelihood with respect to the data x. And our goal is to train some parametrized function, let's call it s theta of x, that matches this guy. So rather than modeling p theta of x, we're going to model this object and we'll call it s theta of x. We still need to be able to match this thing against the real score function of our data distribution, but we're modeling a slightly different object. Everybody okay with this? Yeah.
Is there something like cut off after the log?
Yeah, because I copy and pasted in a sad way, but this fully defines what's going on here. Okay, everybody okay with what we've written? Now, there's nothing very obvious about what we've talked about so far, right? For one, when we talked about p theta of x, we had likelihood as a principle, right, for us to figure out how to pick theta. Over here, it's not obvious for me how to pick theta at all, right? For one, I have no idea what this thing is if I just see some data points, right? I have to figure out some way to approximate that and then to match up s theta of x to it. Second, even if I could train this thing, what is inference here, right? How do I sample an x for s theta of x? That's also different. So really, so far, it's not obvious at all that this makes any sense, but I promise you that it does. Before we get there, though, let's see if we have the same partition problem, right? The partition function was that big blocker. Let's see why this avoids it. Okay, so let's go ahead and plug in the energy function, the x of f theta of x divided by z. So now let's compute the score function for that version of things. The score function, again, is just a gradient with respect to x, log p theta of x. P theta of x, we said, is 1 over z times f theta of x. Take the log of an exp. I just get left with the f theta of x here. Log and exp cancel each other out, right? And I have to deal with the z. There was a 1 over z in front, and now I have minus gradient log z. The minus is from the 1 over z from before that I passed through this. Okay, everybody okay with that? So I have these two terms. Well, this one does have to do with z. That's bad. This is the partition function. But remember, we're taking the gradient with respect to x, not theta. And because we're taking the gradient with respect to x of something that has nothing to do with x, only has to do with theta, this thing is 0. It's just a constant. We're differentiating it with respect to x here. So what I get left is just this guy over here. So this is good, right? The problem we had initially was that we had to recompute the z theta for every new value of theta during optimization. Now it just fully disappears because the score function doesn't actually care about it. It's using the gradient with respect to x. Okay, does this sound good for everybody? Yeah.
Why do we have a minus sign?
Are you talking about here? Well, okay. So sometimes people do it the other way, and they have x of minus f theta of x. And therefore, a large value of it means a small probability and vice versa. I think this was the case for where I got this from. But you can correct that sign over there. Okay, so this is, again, the gradient with respect to x, not theta. And that's what makes the partition function term 0. And therefore, we don't have to deal with it. So all of the optimization that we do now is partition function free. And therefore, it is worthwhile to try to figure out how to use these score functions. Okay, so how are we going to do it? Well, for training, really what we can do here is to say, if we somehow have access to this guy over here, the true score function, I can basically say, okay, well, pick out samples and try to make the scores match up, right? This is literally score matching using mean squared error as my metric, as my loss for this. Everybody agree? Now, granted, we don't know how to compute this yet. We don't know how to get the real values of this, right? So it's pretty hard to optimize this whole guy with respect to theta because we don't know it yet. But assuming we had techniques like that, and we do, then we can use this loss function for training. Okay, so there are techniques. They're literally called score matching. I'll let you do this. And for inference, if I somehow have access to s theta, and it's a good representation of the score function, then there are some really interesting iterative methods that help you actually get really high quality samples just from the score function without knowing the actual distribution. Now, this thing is a very fancy method. It's called Langevin dynamics. What we're going to do here is construct a series of samples that get increasingly close to being accurately sampled from the true distribution. And the series of samples looks like this. First, we're going to iterate. We're going to get some xi, and then we're going to transform it into xi plus 1. We do this for many steps. We are going to use the actual learn score function. That's this guy over here. This is the thing that we trained to get, plus some special constant epsilon here. And then we'll add a little bit of noise in a controlled way, and we'll run this process through repeatedly. Notice that we're using this learn score function a bunch of different times over here. And if you do this many iterations, then it turns out you actually get a sample that represents the original distribution correctly. You can prove this. It's actually a very nice technique, but take it for granted for the time being. Okay, so what's going on here, visually speaking, is something like the following. The score function is these arrows. It's this vector field. And what this really means is that at every point, the score function is telling you, this is where you should go to get to a very high probability area of our space. Now, this is two-dimensional. It's very simple, right? And this is really a mixture of two Gaussians centered here and here. But it's really the same process for anything else. If I've trained my s theta of x, it's really telling me whenever I plug in a point what this arrow looks like and where it's pointing to. And that entire Langevin dynamics thing, it was saying, well, start anywhere as a point and follow these arrows, right? Keep following them, sometimes getting smaller and smaller until you kind of finalize somewhere. And that's a sample from your original distribution. And if you run many such samples, you're actually correctly approximating the true distribution. And you can see that, right? I mean, you're ultimately getting a ton of points from the very high probability region for this Gaussian, and also from this Gaussian, even though your initialization was everywhere scattered around. So everyone see kind of how this process worked for sampling? Now again, we didn't fully implement the formula, but you get the idea. And we didn't really fully talk about how you actually train these arrows. That was the score matching techniques, but the principle should kind of make sense here. Okay, so these ideas kind of need a little bit more work to become practical. They work fine for this toy problem, but you have to do a tiny bit more to actually make really, truly realistic samples for a true data distribution. And that's where we'll kind of get into the whole noising and denoising. But you can kind of sort of see it already, right? Like the little steps that we're taking and adding noise, it's helping us move around until we get to these high probability regions. Okay, now we're out of time, so let's continue this conversation on Thursday. We have a few more slides. Other than that, nothing else. Just remember the presentation proposal is due on Thursday too.